Welcome to another video on the Apply Electronics. Today, I'm going to solve some of the quizzes that we wrote. That was last week. We wrote quiz on the first two chapters. That was chapter 1, which was semiconductors, and then chapter 2, we talked about transistors. So I'm going to solve the questions under that. Okay. So I'm going to start with RP students, that is refining engineering students. So I'll start with the first paper, the first group that wrote group A. Okay. Now, so the first question that was given was question 1. You were asked to state 4 properties of a conductor. So what are the 4 properties of a conductor? So this one, I'm not going to write it. I'll just say what those properties are. And like I said, I'll be sending the soft copy to the course rep. Then the course reps will share it with you, the students. So when you talk about the properties of a conductor, you can think of a conductor, for example, being a copper. So if you have a copper, we know that a copper can conduct electricity easily. So one of the first property, we can say that a conductor is a good conductor of electricity, right? And then the second point is when the resistivities of a conductor, they tend to be very low, right? You have them being around 10 to the power minus 8. So their resistivities are very low. So you can even see why they're able to conduct electricity because of that resistivity that they have. They have very low resistivity. And then the third point is conductors, they tend to have two or three valence electrons, right? Yeah, they tend to have valence electrons of 2. And the last property is that when it comes to conductors, their resistivity tend to increase with increased temperature. So if you are increasing the temperature of a copper, it will end up increasing the resistivity because the electrons, they tend to collide, and then as a result of that, they end up increasing their resistivity. Now, that was for question 1A. Question 1B, with the aid of diagrams, explain reverse biasing. So reverse biasing is a process in which a diode prevents current from passing through it, right? So when it comes to reverse biasing, the PN junction, right, which is where we obtain a PN junction by doping one part of a semiconductor with P-type impurities, and then the other side with N-type impurities. So during reverse biasing, because of the force of attraction between let's say the positive side of the bias voltage, which is being connected to the N region, and then the negative side of the bias voltage is also connected to the P region. As a result of this end up widening the depletion region. So as a result, this prevents the flow of current through the PN junction. But we know that there's tend to be a small amount of current, which we regard as reverse current, which occurs as a result of minority charges. So the minority charges that we have in either N region or P region, they contribute to the flow of current. Now, moving on to the question 2. State 3 ways of connecting a bipolar junction transistor. So this one, I'm going to sketch the various diagram. So we know that if we are talking about the 3 ways of connecting a bipolar junction, we can have, for example, we have common, right? We have, for example, common base connection. Then we have emitter-based connection and the collector-based connection. Now, 2II, illustrate the connections with diagrams. So when it comes to the diagrams, for example, if we have first, I'll start by indicating the we have a resistor, for example. If this is our resistor, we have our resistor here. So if we have our resistor, okay, now let's say this is NPN. So let me make the current to be going out, NPN. So we have the base here, we have the emitter, then the collector. So when it comes to now, we start with emitter-based connection. So when it comes to emitter-based, meaning we think about having an electrode, right? So this our electrode is like a wire. So depending on which terminal device you decide to connect to this electrode, then we name it the connection with regards to that. So if you connect the emitter to this electrode, then we call this common emitter connection. Then we do the same for the same technique. We use the same technique to illustrate common base connection. So in that, in the same, we have our resistor. So I have my resistor here. So again, this is going to be NPN resistor, a bipolar junction resistor. So again, we have our emitter. So let me make it the other way. I'm going to make it rather common collector. Common collector in that case. Okay, let me move it. Okay. We just maintain a common base. Again, we have our electrode here. So if we have here as my emitter is the emitter. I have the collector here. Then this is our base. So we refer to this as common base connection. And then we do the last one, which is common collector connection. So the same thing, we are going to have our transistor here. So this time, I'm going to make this side be the emitter. So this is my emitter. And then here is my collector. And then here is the base. So with this, again, I have my electrode here. So we connect this. So this becomes common collector connection. So that's it for this part. So we move to the next question. Okay, so moving to question now. Yeah, to question 2B. Explain PNP bipolar junction transistors. So explain PNP bipolar junction transistors. So here we have to explain how PNP bipolar junction transistor works. So the way it works when it comes to how the PNP bipolar junction transistor works, again, I'm going to just explain this. So the first requirement is that you make sure that the emitter base junction is connected in reverse, in forward bias, and then the collector base is connected in reverse bias. So the emitter base is connected in forward bias, while the collector base is connected in reverse bias. So as a result of this, we know that if we have PNP transistor, it means that we have two PN regions and only one N region. And the N region, which is in the middle of these two, the two PN regions, it tends to be what? Slightly doped, right? Or lightly doped. So as a result of these two connections that we have done, what happened is that the majority holes which are in the P region side, the P region side, which is related to the emitter, they start to move into the N region, whereby they'll combine with the majority electrons there. But because the N regions is slightly doped, so the holes are able to combine with the electrons. This will end up leading to excess amount of holes in the N region. So as a result of this, the holes which are in the N region, they force their way towards the positive side, the negative side of the bias voltage of the emitter base junction. And then they also move towards the negative side of the collector base junction, right? So as a result of this, you have current flowing through the PNP bipolar junction transistors. So we have that. So I can just sketch a diagram indicating only the current that we tend to have. So here we have current, which is entering the emitter. And then we have current now leaving the base. So we have base current, and then we have collector current. So we have the emitter current being equal to the base current plus what's the collector current. So I see. So we have this. Okay. Now moving to question 3. When it comes to question 3, what is the type of rectification in figure 1? So we have figure 1 here. This is our figure 1. So if you want to talk about the type of rectification, you can see that we are having an alternating voltage, and then a diode, and then a load resistor. So because we are having one diode here, we know that there's going to be what halfway rectification. So this one, question 3 here, A, we have half-wave rectification. So we go to 3B. Now, question 3B. What is the load current and the peak load current if the diode is ideal? Sketch, okay. Sketch the output wave form for 2 cycles. So 2 cycles mean we have what? Each cycle is going 360 degrees, so meaning twice of the 360 degrees will give us 2 cycles. So we have this. Now, how do we calculate the load current and the peak load current? Okay. So with this, what we can do is that we can see that if I have an alternating voltage, right? If I have alternating voltage, so we know that the instantaneous voltage, small letter V, will be equals to maximum voltage sine theta, right? So if we are giving, you can see that in the diagram, we are giving 50. We have 50 volts here. This 50 volts represent the root mean square value, right? So the voltage that we get from the electricity company is the root mean square value, right? So once we have that voltage, then we can calculate the maximum voltage. By using this formula, we know that root mean square value will be equals to 0.707 of the maximum voltage. So if this, so we make the maximum voltage the subject, so I get 50 over 0.707. So what do I get? 50 divided by 0.707. So we get 70.72 volts, right? Volts. So we have this as our maximum. So this means that when it comes to our instantaneous voltage, we know I have 70.72 sine theta. So that's our alternating voltage. So you can see that this voltage is going to be going through the diode, and then from there it passes through the what? It goes through the low resistor. Now with this, because we are dealing with a diode, and then we are also having an alternating voltage as our source. So what we can do is that we can sketch 2 cycles of our alternating voltage. So that's what I'm doing now. So the first one, so indicate here to be 70.72 volts is theta. Here we minus 70.72 volts. Now, for the first cycle, you get this. It's a sine wave, so it's going to be this. So we have something of this nature. Now that we've done that, so the first, we can see that when it comes to the first alternation, which is going to be from here, this thing here is supposed to be, the number here is wrong. To sketch for 2 waves. So here supposed to, this for only one cycle, supposed to sketch for another one. So let me include, there's a mistake here. Here should be 2 pi. So we have here 3 pi. Okay. So, and then we have 4 pi. So here we end up getting okay. So we have something of this nature. Just to make here we have 2 pi, 3 pi, and then 4 pi. So we have an alternating voltage of this nature. Now with this, we can see that when we have the first alternation, which is going to be from 0 to pi. So you can see that part, we have a positive alternation. So as a result, they will be forward biasing. So we can come here. So as a result of forward biasing, I can see now this will act like a closed switch. So we just have something of this nature. So as a result, we are going to get V here will be equals to, based on Ohm's law, right? So the current that will be passing through the current that is going to pass through the resistor, which we call the forward current. So we have IF. So IF is going to be equals to the voltage source over the load resistance. So we can see this is going to be equals to 70.72 sine theta all over the load resistance, which is 4.7 kilo ohms. So we have 4.7 kilo ohms. So we have this divided by 4.7. So that will be 15. So 15.05 10 raised power 3 sine theta. So we come here. This is going to our current here in terms of milli. Okay. So if this is in terms of milli, here what is the same as 50.05 milli. Okay, let me know indicates a milli here. Can just leave it like this. Okay, I know that here will now be 15.05. So we have, so as you can see, the first alternation here, we have this passing through. Now, when it comes to the next alternation, which is going to be, can see the next will be pi less than or equals theta less than or equals to 2 pi. So here, this is going to be what? Going to have reverse biasing taking place. So that means when there's reverse biasing, we know that current is 0, meaning the reverse current is 0. So here we are going to get 0. And then the next one, which is also, can see another alternation. So that one will be what? Again, forward biasing. So this will go through. And then the last one, which will be reverse biasing, so that will be 0. So we have this, right? So you can see that we've indicated the as you can see, we've calculated the load current. Okay, the load current as we are is going to be the same as load current will be equals the forward current, which is 15.05 times 10 to the power minus 3 sine theta. Okay, that's the load current. And then the peak load current. So peak load current is just going to be equals to 15.05 times 10 to the power minus 3. That will get 15.05 milliamps. Okay. So we've come to the end of this video. See you in the next video whereby we'll be solving RP quiz RP 162 quiz B. Okay, so we solve that one on the next video. Bye bye.